Now, in this video, we're going to look at how to conduct a paired t-test. So two sample t-test, but the data is paired. Now, particularly when you're doing these tests, one of the issues that students run into is trying to determine whether the problem is paired or unpaired. Now, if you have different size data sets for your two groups, it can't be paired. Paired literally means for every value in one data set, there is a corresponding value in the other data set. Typically, sort of a before or after situation, or where multiple variables are matched. You generally want to look for keywords in a paired problem, like paired or matched, or things like that. So again, or like this before or after situation, both the person looked at both ads or something of that sort. Now, in the paired case, we have to work from the raw data. So that's an important consideration. If you only have summary statistics, you can't do a paired t-test. So it's always based on the raw data. So as we go through this video, go through this process, we'll show you how to do it by hand, but then we'll also show you, because we have the raw data, how Excel can make this a lot easier for us. All right, so let's look at our problem. We've got 44 sixth graders were randomly selected from the school district, and they were divided into 22 matched pairs. So notice these are different students, but they're matched. Generally, they're matched. In this case, they're being matched to have similar IQ scores, but sometimes they can be matched for multiple reasons. But here they're saying they're matched by this one condition. So one member of each pair is randomly selected to receive special training, and then all of the students were given an IQ test. And the idea here, again, is to see if, generally they do these things to see if the training will improve the scores. The results are summarized below, and we want to know if the results provide evidence that the training changed the student's performance on the test. So again, this is not IQ tests are not, they're trying to measure some inherent quality, but they don't actually necessarily only measure that. They also measure things like training and preparation and so on. And so what we're trying to see is if those scores change. All right, so we're going to use a standard level of significance. We should state our null and alternative hypotheses before we do anything else. The null is that, now if the two groups are the same, typically we use the delta, because that stands for, it's the Greek version of D, and D stands for the difference. And essentially we're looking at the differences to see if the training versus the no training had a change. Now, because we're not doing an independent test, we're not calculating one mean and then comparing it to the other mean. We're actually calculating the individual differences between each individual pair, and then calculating essentially a single sample t-test. So we notate this a little bit differently than we do the independent case. And then in this particular case, we want to know if the differences are, if the training made a difference. So we essentially want to know, again, we're going to have to be careful about how we do the subtraction. But essentially we want to know if the training differences were better. So if we subtract training minus no training, and the training scores, the students that received the special training were higher, then those differences should overall be positive. And so that's what we want to test. If the training improved the performance, then those scores should be higher. And if we subtract training minus no training, then we will get a positive difference. Now, you do have to be careful, because you could subtract in the other order, in which case you would be testing to see if the differences were negative. It's an equivalent and perfectly valid way of doing it. You just need to be consistent with what we're doing here. select your inequality based on the order that you intend to do the subtraction in. All right, so that's our null and alternative hypotheses. And again, essentially, this is a single sample t-test once we do the differences. So I've copied this over into Excel, and so let's go over to Excel to actually do the calculations. Now, in order to make things go a little bit faster, what I've done is I've actually laid out the table. The table was put in 2 rows in order to make it fit onto the page better, but I've laid them out here side by side so that all the data is laid out, training in one row and no training in the other row. Now, the order that you do these calculations in doesn't matter. You could recopy these into columns, but since it was presented in the problem that I copied in this horizontal order, I'm just going to leave the data in that horizontal order. Now, what we're going to calculate is the differences. And I'll do this by hand, and then we'll show you again the shortcuts. The differences are then going to be the training value, so the one that we think is going to be better, minus the no training. And then we're going to copy that formula all down the table. And then the way that we would go ahead and calculate this would be, we would calculate the mean, which is the average of the differences. And then the standard deviation of the differences. And then our standard, or let's see, our sample size, N is 22. They told us that in the problem. So the standard error is then the standard deviation divided by the square root of N. And then our test statistic is, so again, the test statistic, it's typically the sample difference minus the hypothesized difference. Typically, that hypothesized difference is 0, so it's just the mean as it is here. But you can hypothesize other values. You can say, well, we don't really care if it only minimally improves the scores. We only want to like spend the money on if it improves the scores more than a certain amount. But in this case, we're just looking to, does it do any improvement? And so that's the mean divided by the standard error to get our test statistic. And then finally, we would convert that to a p-value using our t.dist. Now, this is a greater than, so we're going to use the 2t, x, and then our degrees of freedom is n minus 1. And so this is greater than 0.05. So we fail to reject the null. And so there is not sufficient evidence to conclude that the training made a difference. So that the students that receive the training are not scoring appreciably higher, statistically higher than their students, their classmates who started with equal IQs, that did not seem to improve anything at all. Okay, so that was doing it the by hand way, but because we have the raw data, we can actually do this in a couple of different ways without having to do that. So we can go straight to the p-value if we use the function t.test. Now again, we can't use this function. Notice it asks for an array. We can't use this function if we do not have the raw data. So the array is going to be the training data for array 1. And then for array 2, it's going to be the no training data. And then the tails is going to be a one-tailed or two-tailed test. We are doing greater than, so that is a one-tailed test. And then depending on the size of the differences, this will automatically go to the right tail or the left tail. And then is it paired or pooled or unpooled? So equal variance is the pooled case. Unequal variance is the unpooled case. Well, it's not either of those. We want the paired one. So we're going to pick 1. Oh, I did the two-tailed one. I shouldn't have done the two-tailed one. I should have done the right-tailed one. See, that's not me paying attention. There we go. It doesn't change our conclusion any, but it's important to have the right p-value. Okay, so that's that version of it. So you can do it with the t.test. Now, you can also get a few more statistics out of this by using the data analysis tool pack. And at the very bottom, we have t-tests. We also have z-tests. We're not going to look at the z-test. Feel free to play around with it. But it's essentially one of these independent tests, but for variances which are known. In our case, we're going to do the t-test 2-sample for means. This is the paired version. Variable 1 range. Now I'm highlighting the labels here, so I'm going to have to check the labels box. And then group 2. Labels. Hypothesized mean difference is 0. That's the null hypothesis, that there's no change. Our alpha value, and we're going to put the output range. I'm going to put it down here on the bottom, so it's kind of out of the way. And then we're going to hit OK. Now, the nice thing about the data analysis tool pack is it's a good way to confirm some things. So for instance, we calculated our test statistic right up here, and we calculated our p-value, and both those values are right here. We can see it matching, but it also calculates a bunch of other statistics for us in case we needed that information. It's going to automatically produce some additional output. It gives us both the one-tailed and the two-tailed values. It gives us the correlation in case we were, doing a scatter plot type analysis. And it also gives us means and variances of both data sets separately. So it gives us a little bit more information. We don't necessarily need these things, but it does give us a little bit of additional information that just the t.test function doesn't give us. We don't have to decide, for instance, whether we're doing one-tailed or two-tailed with the data analysis tool pack, because it gives us both. And then after we're done calculating, then we can worry about that. So it is another option that's available to you if you have that installed.